Hi, how are you doing? Today we are going to talk about chapter 6. So let's get started. So today we are going to talk about the normal curve. And these are the objectives. Use a probability density curve to describe a population. So basically, these are all frequency distributions or histograms. So we on the vertical axis, on each of these, we have the relative frequency or probability. On the horizontal axis, we have the different groups. Notice in the top diagram, for example, the first group is from 0 to 1, next group is from 1 to 2, then 4 to 3. On top of each of these groups, we have vertical rectangles. The heights of the rectangles indicate the relative frequency or proportion of the samples which are between 0 to 1, for example. Similarly, the height of the second rectangle represents the relative frequency or the proportion of the entire sample or population that is between 1 and 2. So the height is the relative frequency or probability, and the width is the width of the group. This type of diagram is called a histogram when the bars, adjacent bars touch each other. So it's a frequency histogram because the adjacent bars, the bars next to each other, they touch. Heights of the bars represent relative frequency. Consider a data set consisting of vehicle emissions. We can visualize this data with a relative frequency histogram. Class intervals are chosen so that each rectangle represents a reasonably large number of vehicles. So on the horizontal axis, you have the sizes of the particles which are coming out from the tailpipes of the car or the exhaust of the car. So for the first group, it is between 0 and 1. The particle sizes are between 0 and 1. For the second group, the particle sizes are between 1 and 2, or so forth. Vehicle emission is a continuous random variable. What is a continuous random variable? It can contain decimal values. That is, for example, in the first group, the size of the particle can fall anywhere between 0 and 1. Recall that a continuous variable is one whose variables can be any value in some interval. That means decimal values are possible. For example, in the first group, a particle can be sized 0.875. Another particle can be sized 0.925, for example. Suppose that the sample of vehicles was very large, consisting of millions. That is the second diagram. Okay, because the amount of emission is a continuous variable, there will be a reasonably large number of vehicles for each rectangular, even for small class intervals. So what is the difference between the top diagram and the bottom diagram? The bottom diagram is same relative frequency versus the width versus the dimensions or sizes of the particles coming out, but here the width of each group has been reduced. The reason the widths have been reduced is because there are millions of vehicles, and even if we reduce the width of the size of a particle in a group, that is the base of each of these rectangles, we will have large number of particles falling in each group because there are large number of vehicles, even with a smaller width. So basically, the width of the rectangles have been reduced by increasing the number of groups of sizes. But also notice these rectangles, adjacent rectangles touch each other. The heights of the rectangles represent the relative frequency or proportion of particles in each group. Okay, and now we can join the top roofs of these rectangles and get a smooth frequency distribution curve, which is also called a probability density curve. Okay, such a histogram would look smooth and could be approximated by a curve. The curve used to describe the distribution of this variable is called a probability density curve. The probability density curve tells what proportion of the data falls within a given interval. The area under the probability density curve between two values A and B represents the proportion of population whose values are between A and B. Okay, so the area under the curve between 3 and 4, which is 0.17, means, in one aspect, it means 17% of the vehicles have emissions coming between 3 and 4. Okay, the proportion of the population with values between 3 and 4 is this area, which is 0.17. So at 3, we draw a vertical line to meet the probability density curve, and at 4, we draw another vertical line to meet the probability density curve. The area under the curve represents the proportion of vehicles that are proportion of particles that are between 3 and 4 in dimension. It can also be interpreted as the probability that a randomly selected value from the population is between A and a B. So what does it also mean? It means there is a 17% probability that a randomly selected particle will have a size between 3 and 4. Okay. The region above a single point has no width. There is no width. Therefore, if x is a continuous random variable, probability of x equal to a equal to 0 for any number a. And the reason is very simple, because there is no width at the particular point a. We are drawing a single vertical line. We do not have any horizontal width. Remember, the area of a rectangle is height times width. In this case, width is 0. Therefore, probability at particular value of x equal to a is equal to 0 because there is no width. This means that probability of x between a and b is same as probability x between a and b. Both a and b are inclusive in the second one. That's why they have an equal to sign. That means that if you include a or if you include b, it will not make any difference, because probability of x at equal to a and probability of x equal to b both equal to 0. So whether or not you include the boundaries a or b does not make any difference. For any probability density curve, the area under the entire curve is 1, because this area represents the entire population. Remember, the sum of probabilities is always equal to 1 or 100%. Therefore, the area under the probability density curve, which is basically representing probability, is equal to 1, total area. Consider the probability density curve with some areas indicated. Find the proportion of the population is between 0 and 1. Now, if you look at the diagram, the area under the probability density curve between 0 and 1 is 0.63. So the proportion of particles which will fall between 0 and 1 is 0.63. That's the answer for part A. Part B, the probability that a randomly selected value will be between 1 and 2. So that probability area under the curve is 0.23. So there is a 23% probability that a randomly selected value will be between 1 and 2. That's the answer for part B. Part C, the proportion of population is between 0 and 2. So between 0 and 2, you add the two areas, 0.63 plus 0.23 is 0.86. So there is 86% of the population will fall between 0 and 2. That is the answer for part C. For part D, the probability that a randomly selected value will be greater than 2. We already know that the probability that a randomly selected particle is between 0 and 2 is 0.86. obtained by adding the two areas. So we also know that the total area under the probability density curve is 1. Therefore, probability that a randomly selected particle is greater than 2 is 1 minus 0.86, which is 0.14. This is the answer for part D, as in David. A uniform distribution is one in which the values in any region are equally likely. The probability density curve for a uniform distribution is horizontal line. It is called uniform. That means probability at any selected point will be the same. That's why the probability density curve is a flat line. Imagine that when a traffic line turns red, okay? It stays red for 30 seconds before turning green, okay? If you pull up the light when it is red, the amount of time you will wait before the light turns green is uniformly distributed 0 and 30. Okay, so at 0, the probability is 1 over 30. At 30, the probability is 1 over 30. After 30 seconds, the probability becomes 0 because then it will stay green. Okay, so the height is 1 over 30 and the width is 30 minus 0 is 30. So 30 minus 0 is 30, with the width times height is 1 over 30. 30 multiplied by 1 over 30 is 30 divided by 30, which is 1. So the height is 1 over 30 because the length is 30. Entire area must be equal to 1, as we showed, because 30 is the width, waiting time, multiplied by the height, which is the probability, is 1 over 30. 30 times 1 over 30 is 30 divided by 30. Total area under the curve is 1. Probabilities for the uniform distribution are straightforward. The probability of an event corresponds to the area of the rectangle. Find the probability that the waiting time is between 5 and 15 seconds. Area is, again, width times height, or width times length. So width in this case is 15 minus 5 is 10, multiplied by the height, which is 1 over 30. It's uniform, so it's 1 over 30. So 10 multiplied by 1 over 30 is 10 over 30, or 1/3. So the probability that waiting time is between 5 and 15 is 1/3, or 0.333, 33.3%. The waiting time as a bus stop for the next bus to arrive is uniformly distributed between 0 and 10 minutes. So the width is 10 and the height is 1 over 10. Find the probability that the time is less than 3 minutes. Less than 3 minutes between 0 and 3. The width is 3 and the height is 1 over 10. 3 times 1 over 10 is 3 over 10, or 0.3. Find the probability that the waiting time is greater than 6 minutes. Here the width is 10 minus 6, or 4, and the height is still 1 over 10. So the area or the probability is 4, which is the width, because 10 minus 6 is 4, times 1 over 10, which is the probability, is 4 over 10, or 0.4, 40%. Find the probability that the waiting time is between 3 and 8 minutes. Here the width is 8 minus 3, 5 multiplied by the height, which is 1 over 10. 5 multiplied by 1 over 10 is 5 over 10, or 0.5. 50% probability that the waiting time is between 3 and 8 minutes. Okay. Use a normal curve to describe a normal population. Objective 2. Probability density curves come in many varieties depending on the characteristics of the population they represent. Many important statistical procedures can be carried out using only one type of probability density curve, called a normal curve. As you can see, it is like a bell. Okay, it's a bell or an inverted U curve. There's only one point on the horizontal axis which has a highest height, or the highest relative frequency distribution. And the left half of the curve, that is, if you draw a vertical line at the point from the base where the frequency, relative frequency is the highest to the peak, the left half of the curve is equal to the right half of the curve. So the normal curve is a bell-shaped curve, is symmetric. Left half is equal to the right half. Normal distributions have one mode. What does it mean? That means there is only one point on the horizontal axis which has the highest height or relative frequency, and therefore it has got one mode. Normal curves extend infinitely far both to the right and to the left. That means this curve comes close to the horizontal axis but never really theoretically touches it or crosses it, on the right as well as on the left. So on the right, the normal curve extends to a very large number, which is a very large number on the right, which is usually infinity. Similarly, on the left, the normal curve comes very close to the horizontal axis, but never really touches it, cuts it, or crosses it. Okay, and it extends to negative large number or negative infinity on the left. Population mean determines the location of the peak. The population standard deviation measures the spread of the population. Therefore, the normal curve is wide and flat when the population standard deviation is large, and tall and narrow when the population standard deviation is small. The mean and median of a normal distribution are both equal to the mode. So let's look at the diagram on the left. Here, both the curves have the same mean, where the peak is the highest for both the curve, which is equal to 0. But the dashed curve is more spread out than the solid curve, because the dashed curve has a higher population standard deviation of 2, whereas the solid curve has a population standard deviation of 1. Remember, mu is small m in Greek language. Because we are dealing with population, it represents population mean, or small m in Greek language, mu equal to 0. And sigma, which looks almost like a 6, okay, sigma is small s in Greek language, is population standard deviation. So what we learn is, if the standard deviation is higher, the curve will be more wider, okay. Also, let's look at the diagram on the right-hand side. Here, the means are different because the peaks are at the different places for the two different curves. The first curve, the peak is at mu equal to 0. The second curve, the peak is highest at mu equal to 5. But they are both spread out about the same. So the population standard deviation is same for both, sigma equal to 1. So the width of the distribution is given by the population standard deviation. Normal distribution follows the empirical rule. What does it mean? At the center where the peak is the highest is mu. You add one standard deviation to the mean on the right to get mu plus sigma. You subtract one standard deviation from the mean to get the point mu minus sigma on the horizontal line. From there, you draw a vertical line. From mu plus sigma, you draw the vertical line. According to empirical rule, 68% of the data will fall between mu minus sigma and mu plus sigma. Similarly, if you spread out two standard deviation on the right, mu plus 2 sigma, and two standard deviation on the left of the mean means you subtract mu minus 2 sigma, you cover 95% of the area. And if you go 3 standard deviation on the right and 3 standard deviation on the left, approximately 99.7% of the data will fall between mu minus 3 sigma and mu plus 3 sigma. And here they show calculation to prove that this is the case. Okay, I will not go into this. Okay, we do not know all the values of the population of the body temperature, but because the sample is bell-shaped, we approximate the population with a normal distribution mean equal to 98.2. Standard deviation is 0.6. And if you add, say, mean plus standard deviation is 98.2 plus 0.6 is 98.8 on the right, on the top diagram. And on the left of the mean, you subtract 98.2 minus 0.6 is 97.6. So you draw a vertical line at 97.6 and you draw another vertical line at 98.8. Okay, and let them meet the normal curve. So from empirical rule, approximately 68% of the data will fall between 97.6 and 98.8. And that's what they shows. Okay, so 5,904 points out of 8,670 points fall between 97.6 and 98.8, which is the ratio is 0.68 or 68%. So this shows that empirical rule is true in this case. Areas under the normal curve. The areas under the normal curve represents a proportion of the population or can be interpreted as probability. It is therefore necessary to find areas under the normal curve other than those specified by empirical rule. So empirical rule is valid for mu minus sigma, mu plus sigma, mu minus 2 sigma, and mu plus 2 sigma, for example. But what about other areas? which are not connected with mu minus sigma, mu plus sigma, or mu minus 2 sigma, mu plus 2 sigma. We have to find the areas under the normal curve because the area is the probability or the proportion of times that a particular random variable will fall between the two vertical lines, okay? So we are not going to use, but I'll show you the calculation for z-scores. Z is a standard normal variable. Basically, we take a value of x and subtract the mean of the population from that. So the numerator in the definition of z is x minus mu, means how far the number is located from the mean of the population. And then you divide it or standardize it by the standard deviation. So basically you get a z-score. The z-score, if it is positive, that means x is greater than mu. That means that z-score shows how many standard deviation above the mean is the number x located. If you get a z-score of negative, that means x is less than mu. That negative z-score shows how many standard deviation the number x is below the mean. Okay, so we will do this using our calculator. Compact fluorescent bulbs are more energy efficient than incandescent bulbs, but they take longer to reach full brightness. The time that it takes for a compact fluorescent bulb to reach full brightness is normally distributed. Mean, that means mu, equal to 29.8 seconds and sigma, standard deviation of 4.5 seconds. Randomly selected bulb takes 28 seconds to reach the full brightness. Find and interpret the z-score for x equal to 28. Notice 28 is below the mean 29.8. So first we will find out how far x is located from the mean. That is 28 minus 29.8, which is minus 1.8. Then we will standardize it or divide it by the standard deviation. So it is minus 1.8. We are using our calculator. 1.8 divided by the standard deviation 4.5 is 0.4, but we know it is negative. So what does it mean? That means the x value of 28 is located 0.4 standard deviation below the mean. Okay. Z-score of negative means below the mean, because the number 28 is lower than the mean 29.8, that is on the left of the mean. So it is below the mean by how many standard deviation? 0.4. Okay, we are not going to use tables, so I'm going to skip this. TI-84 plus. Okay. On TI-84 plus calculator, the normal CDF command is used to find the areas under a normal curve. 4 numbers must be used as input. First is the lower boundary. Lower bound means lower boundary of the area. The second entry is the upper bound or boundary of the area. The last 2 entries are mean and standard deviation. How do I find normal CDF in my calculator? I press the second key on the top left, second, and then verse key, which is in the third row. Second and verse, and then scroll down to number 2 by the down arrow key. Go to normal CDF so that the cursor is lined up with normal CDF. Cursor is the black rectangle, and hit enter. Okay, and it is asking for a lower. Most of the time, the lower will be minus 1 E99. Minus means negative on the left. E means exponent, that is means 10 to the power, and 99 means 10 to the power of 99, or 1 followed by 99 zeros, which is a very large negative number on the left. Okay. So find the area to the left of z equal to 1.26. So as shown, this is a standard normal curve. At the center, z is equal to 0. And we want to find the area to the left of 1.26 because 1.26 is positive on the left of the mean. For a standard normal curve, the mean is 0. So at the peak is the highest for a standard normal curve. Z is equal to 0. So z equal to 1.26 falls to the right of the mean on the horizontal line, 1.26. So my lower boundary is where I'm starting in the left. Okay, it's a very large negative number on the left, where the curve stretches to the left. And as I told you in the calculator, it's already set up as minus, means negative on the left of 0, 1, E99. E stands for exponent. That means 10 to the power of 99. Very large number on the left is my lower boundary. My upper boundary is 1.26 because I'm starting from the lower and stopping at the upper boundary of 1.26. Okay, what is my mean? This is a standard normal curve. Mean is 0, standard deviation is 1. These are already set up in the calculator. You don't change it. And then you scroll down with the down arrow key of the calculator to paste and hit enter once. Whenever you see paste, you have to hit enter twice. And the area is 0.8962. What does it mean? It means the probability that Z will have a value below 1.26 is 89.6% or 0.8961. A study is reported that the length of pregnancy from conception to birth is approximately normally distributed. Mean is 272, sigma is 9. Now we are not dealing with a standard normal curve. Okay, what proportion of pregnancies last less than 259 days? Now 272 is the point in the center which has the highest peak. Notice 259 is below 272. Right? 259 is less than 272. And further, we want proportion of pregnancies that last less than. So less than means on the left of 259. So again, we do the same thing. Second button on the top left, then verse on the third row, then scroll down to number 2, normal CDF, and hit enter. My lower is still minus 1 E99. My upper is now 259. So I type in 259. My mean is no longer 0 because it's not a standard normal curve. My mean is 272. So mu is 272. Type 272 after the colon. My sigma is not 1 anymore. It's 9. And then go to paste and hit enter and enter. And the answer is 0.074. What does it mean? It means 7.4% of the pregnancies will last less than 259 days. Okay. Here the question is what proportion of pregnancies last longer than 280? So 272 is the mean. Number 280 is greater than 272. It's on the right of the mean. So that's why they draw a vertical line at 280, which is on the right of the mean 272. And we want pregnancies that last longer than what proportion? Than 280. Longer than means on the right of 280. Now we have to do something different. So we do second verse again. Go to number 2. By the down arrow key, you scroll down to number 2 and hit enter. Now the lower is no longer minus 1 E99. We always start from the left to the right. My lower is now 280 as shown in the diagram. So I type in for the lower 280. What about my upper? It's a very large number on the right-hand side. Remember, I told you it's a 1 infinity. So it's 1 we will type first. Then we have to get the exponent because 1 followed by 99 0. So 1 and then exponent. How do I get E, small capital E? I press the second button on the top left corner after 1. Okay, in the upper line. And then comma. Where is comma? Comma is on top of 7. Second comma gives me the E. Okay, capital E. And then 99. That's my upper. My mean is 272. My standard deviation is 9. I do not change those numbers from the last problem. And I go to paste and hit enter and enter. And the answer is 0.187. What does it mean? 18.7% of the pregnancies will last more than 280 days. And the length, same data, mean and standard deviation does not change. Pregnancy is considered full term if it lasts between 252 and 298. So the lower boundary is 252, the upper boundary is 298. So second verse, then scroll down to normal CDF, hit enter. My lower is now 252. My upper is 298. I do not change the mean and the standard deviation. I go to PEST, hit enter and enter. What does it mean? 98.5% of the pregnancies will last between 252 and 298 days. Okay, forget about Excel. We're not going to use Excel. Find each of the following. Okay, we will do one or two. Normal population has the following mean and standard deviation. Mu equal to 3, sigma equal to 1. Find the proportion of population that is less than 1. Remember, 3 is in the center, 1 is less than 3 on the left of the mean, and we want farther to the left of the number 1. So we go second verse, number 2. Okay, we are starting from a very large number on the left-hand side. So we need that minus 1 E99. This minus sign in the lower is the minus next to the enter, not the minus on top of plus. So hit that minus next to enter, then the number 1. Then I have to get that E, which is I do by second, and then comma, which is the key on top of 7. Second comma will give you the E99. So minus next to enter, then 1, then second button, then comma button gives you the capital E, then 99 is the lower boundary. My upper boundary is less than 1. So boundary is 1, upper. Mean is 3. Standard deviation is 1. And I go PEST, enter, and enter. And the answer is 0.022. Okay, did they give the answer? No. Okay, we will do another problem. This is the bottom right corner. Normal population has the following mean and standard deviation. Mu equal to 52, 56. Okay, let's do the one on the top right. Normal population has the following mean and standard deviation. Mu is 40, standard deviation is 10. Find the probability that a randomly sampled value is greater than 53. 40 is in the center, 53 is on the right of 40, and further we want the area to the right of the 53 under the normal curve. So our lower boundary is 53, upper boundary stretches to a very large number. So second verse, okay, number 2. My lower, I'm starting from 53. My upper is a very large number on the right-hand side. So first I type 1, positive 1, because it's on the right. Then second button on the top left, then comma button on top of 7, which gives me the E99. My mean is 40. My standard deviation, sigma, is 10. I go down to PEST and hit enter and enter. And the area is 0.096. So there is a 0.0968 or there is a 9.68% chance that the sample value will be greater than 53. Okay. Tables we are not going to use. Okay. Find the value from a normal distribution corresponding to a given proportion. So the area will be given. We don't know the unknown. Here the point to note, the area or the proportion should be on the left of the unknown value of X under the normal curve. Okay. So we are going to use in norm. Second verse and then number 3 in norm. Okay. Find the scores on the IQ test are normally distributed, mean equal to 100, standard deviation is 15. What score separates the upper 2%? Upper 2% means on the right, the area under the curve is 2%. So what is the area on the left? Is 100 minus 2 or 98, or in decimal it is 0.98. We have to work with the area to the left of the unknown X value. So we have to plug in 0.98, not 0.02, which is the area on the right. So we go second verse 3. Area to the left is 0.98, bottom 98%. Mean is not 0, mean is 100. Standard deviation is 15. And we call down to PEST. Remember, anytime PEST, we have to hit the enter button twice. Enter and again enter. And the answer is 130.81, which they rounded to 131. What does it mean? Only 2% of the scores will be on top of 131, or 98% of the scores will be below 131. The normal mean of 100 standard deviation. Find the IQ square that separates the middle 90%. The area in the center is 0.9. We have been asked to find x1 and x2. Now, if the area in the center is 0.9, that means the area left in the two tails on the left and on the right is 1 minus 0.9, which is 0.1. Now, I told you the normal curve is symmetric. That means the total area in the two tails is 0.1. Then you divide it by 2 into two equal parts. Area in the left tail is 0.05. Area in the right tail is also 0.05. Why? 0.1 divided by 2 is 0.05. Now we know the area in the left tail is 0.05. We want to find the value x1. So second verse, number 2, 3. Number 3 in norm, because I know the area to the left is 0.05. I know the mean is 100. Standard deviation is 15. I paste, enter, and enter. And that value is 75.32. That means 5% of the scores are below 75.32. How about x2? How about x2? We know the area in the center is 0.9. Area in the left tail is 0.05. So area to the left of x2 is 0.9 in the center, unshaded area, and shaded area on the left tail is 0.05. So 0.9 plus 0.05 is 0.95. So I go second verse, number 3. Now my area will no longer be 0.05. It will be 0.95. Mean is, we do not change the mean and the standard deviation. We paste, enter, and enter. And that's 124.67, which they rounded to 125. We're not going to use this. Okay. Let's do one on the bottom right. Normal population has a mean mu equal to 27. Standard deviation is 12. Find the values that separate the middle 60% from the rest. So area in the center is 0.6. What is the area in the two tails? Is 1 minus 0.6. 60% is 0.6 in decimal. 1 is 100% area. 1 minus 0.6 is 0.4. That is the area in the two tails. Now take that 0.4 and divide it by 2. 0.4 divided by 2 is 0.2. So area in the left tail is 0.2. So we find the number x below which 20% or 0.2 will fall. So second verse 3, area is now 0.2, area in the left tail. And the mean is 27. Standard deviation is 12. I go down to paste, enter, and one more enter. I get 16.9. So what does it mean? 20% of the population will fall below the score of 17. Okay. How about the other side? Now we have 20% in the left tail, 60% in the middle. 0.2 plus 0.6 is 0.8. 80% of the scores are below that second number, x2. So second verse 3. Area is now 0.8. 27, 12 do not change. Paste, enter, and enter. 37.09. Or what does it mean? It means 80% of the scores will be below 37. Okay. Stop share. Now let's go to 6.2. Okay, 6.2. Sampling distribution and the central limit theorem. sampling sample mean, central limit, compute probabilities involving sample means, construct the sampling distribution of a sample mean. I'll give you a brief background to this So previously we were plotting X or the random variable, such as person's score, person's height on the horizontal axis. And on the vertical axis, we have the relative frequency or probability. Here, in this section of chapter 6, we are dealing with the sample mean X bar on the horizontal axis and relative frequency or probability on the vertical axis. Because we are dealing with sample mean or X bar, that probability distribution is called sampling distribution of the sample mean. So, like I said, I want to say find out the mean age of population of all students at Wilmington University. Not possible, because contacting all the students comprising the population will take too much time and effort. So instead of doing that, suppose I select 100 samples of size 50 each. 100 samples of size 50 each. In each sample, I ask each student, what is your age? So each sample will give me 50 ages. I add those 50 ages, divide by 50. I get a sample mean age X bar. So in this diagram that you see on the screen, the rectangle indicates the entire population of students, for example, and each of these oval shape inside the rectangle is a sample of size 50. Each of them gave me a value of X bar. So now I have 100 values of X bar. Why? Because I have 100 samples of size 50. So I have 100 values of X bar. Okay, I can divide these 100 values of X bar into groups of certain width. Okay, and I put them on the horizontal axis. Say the smallest age is, just for the heck of it, is 20. So I can have a group sample mean between 20 and 25 on the horizontal axis. The next sample group mean will be between 25 and 30. Next one from 30 to 35, and so forth. So I've divided the sample means into groups, starting with 20, which I assumed is the lowest, and going, say, all the way up to 50. So I have groups between 20 and 25, 25 to 30, etc. And then I draw a vertical rectangle on top of each of these groups on the horizontal axis. So the heights of the rectangles will indicate what proportion of these 100 samples fall between 20 and 25. What proportion of the sample means fall between 20 and 25. That is the height of the rectangle. And remember, the rectangles are each touching one another. Okay, and so we join the top roofs of the rectangles and get a bell-shaped curve, like an inverted U. This time sample mean on the horizontal axis, relative frequency on the vertical axis. That bell-shaped curve, which is sample mean on the horizontal axis, is called the sampling distribution or probability distribution of the sample means. If several samples are drawn from a population, they're likely to have different values for X bar. Because the value of X bar varies each time a sample is drawn. X bar is a random variable. For each value of the random variable X bar, we can compute a probability. The probability distribution of X bar is called the sampling distribution of X bar. Why it is called sampling distribution? Because remember, we have sample means on the horizontal axis and we have relative frequency on the vertical axis. So probability distribution of X bar, in other words, it is called sampling distribution of X bar. So they go through an example. Tetrahedral dice are shaped like a pyramid with 4 faces. Each face corresponds to a number. 4 faces. Tetrahedral means having 4 faces. So 1, 2, 3, and 4. Tossing a tetrahedral die is like sampling a value from the population 1, 2, 3, and 4. Which number will land up? We can find the population mean and population standard deviation. Mean is given by, you add the 4 numbers, divide by 4 is 2.5, and then you calculate the population. Standard deviation is 1.118. Notice there are 4 numbers, very small number of numbers, but still it's a population. Why? Because there are only 4 sides to the tetrahedral die. Suppose that a tetrahedral die is tossed 3 times. The sequence of 3 numbers observed may be thought of as a sample of 3, size 3, because you're tossing the tetrahedral die 3 times. We may get samples such as 111, 112, 113, and so on. And this is an entire table of what numbers we can observe. Okay, the mean of each sample is given in bold column X bar, X bar, X bar. Okay, if you add all these sample means, okay, and divide by the number of samples, which is, I believe, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Total number is, what is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 4 times 16, 64 possible samples. If you add all the 64 values of X bar, add all of them, the numbers in bold, and divide by 64, you will get the mean of all the sample means as 2.5, which is equal to the population mean. Remember, the population mean is also 2.5. And the standard deviation value comes out is standard deviation of this population of X bar. Again, it's population because this is all the 64 possible combinations possible. The standard deviation works out as 0.645. Now, we noticed the mean of the sample means is 2.5, which is also the population mean. But how is the standard deviation of the sample means related to the standard deviation of the population? So this is what we find out. The mean of the sampling distribution, I'm reading the blue lines. The mean of the sampling distribution is denoted by mu X bar and equals the mean of the population. Mu X bar equal to mu. The standard deviation of the sampling distribution, sometimes called the standard error, is denoted by sigma X bar and equals the standard deviation of the population divided by square root of the sample size. So sigma X bar is equal to sigma divided by square root of n. Among certain students at a college, the mean number of hours television watched per week, mu, is 10.5, and standard deviation sigma is 3.6. A simple random sample of 16 students is chosen for the study of viewing habits. Let X bar be the mean number of TV watched by the sample students. Find mu X bar and standard deviation sigma X bar of X bar. Now we know mu X bar is equal to mu equal to 10.5 and sigma X bar equal to sigma, which is 3.6 divided by square root of the sample size, which is square root of 16, which is 4. So it's 3.6 divided by 4 is 0.9. Okay, here is another question, mean standard deviation. Mean is 6, sigma is 4, mu X bar is equal to mu equal to 6, and sigma X bar is equal to sigma divided by square root of sample size, or 4 divided by square root of 25. So sigma X bar is 4 divided by square root of 25, which is 4 divided by 5, which is 0.8. Okay. So we will not go into this. What is this? Consider again tetrahedral die example. The sampling distribution of X bar can be determined from the table of all possible values of X bar. The probability. Okay, so basically they're noticing how many times each of these X bar occurs, and X bar can have values between 1 and 4.0. Okay, the probability of occurring 1 is only 1 out of 64, is 0.016. 1.33, how many times 1.33? It must be occurring 3 times. So 3 out of 64 is 0.047, and so forth. So basically you have a list of X bar, possible values of the sample mean, and the corresponding probability, which is obtained by calculating or by looking through and finding how many times it occurs among 64 samples. For example, as I explained, 1 appears only once, and 1.33 appears twice. So the probability of X bar equal to 1 is 1 out of 64 or 0.016. Probability of 1.33 is 2 out of 64 is 0.047 and so forth. Okay. And if you plot, okay, on the top, oops, what happened? Give me a minute. What did happen? I didn't change anything. No, not this one. Oh, we did this. Just give me a minute. Okay. So let's look at the other one. Yeah, it is. Okay. So on the top, you have the values of X. That is the, remember there are 4 sides, 4 numbers, 1, 2, 3, and 4. Then the corresponding probability for each of them is 0.25. So on the top, you have the probability distribution of the population of 4 numbers, each having a relative frequency of 1/4 or 0.25. So that's why it's a uniform probability distribution for the population on the top. Now from that, you're drawing samples of size 3. And you draw in the denominator, in the bottom diagram, I should say, on the horizontal axis you have the X bar values, and on the vertical axis you have the relative frequency. Notice the population, the 4 numbers, it's a uniform distribution. But look at the bottom, the probability distribution of X bar, or sampling distribution of X bar, is almost a bell-shaped. You can join the top groups and get a bell shape. The probability histogram for sampling distribution of X bar with sample size 3 is obtained from the sampling distribution on the previous slide. The probability histogram for the sampling distribution, which is the second curve on the bottom, looks a lot like a normal curve, whereas the probability distribution for the population on the top is a uniform probability distribution. Remarkably, it is true that for any population, if the sample size is large enough, the sample mean X bar will be approximately normally distributed. For a symmetric population like a tetrahedral die population, the sample mean is approximately normally distributed even for a small sample size like n equal to 3. Here, on the top right, they're showing the population probability distribution. On the 3 curves in the bottom, they're showing the effect of the sample size. Look at the population probability distribution. There is one group on the left which has the highest relative frequency, and then there are other groups which have smaller relative frequency on the top. So this curve is skewed to the right because there are too many numbers on the high side. Skewed to the right, or positively skewed, the population on the top. But then you are drawing samples of different sizes from this positively skewed distribution. When you draw a sample of size 3 on the bottom left, it's still skewed. This is the probability distribution of X bar, or sampling distribution. Then you draw a sample of size 10. Again, it's skewed to the right approximately. But then when you draw a sample of size equal to 30, look at the probability distribution of X bar on the 3rd curve on the bottom right. Okay, so when the sample size becomes 30, the probability distribution of X bar becomes approximately bell-shaped. So in the last paragraph, the size of the sample needed to obtain approximate normality depends mostly on the skewness of the population. In practice, a sample of size n greater than 30 is large enough. So then we come to the central limit theorem. Let X bar be the mean of a large n greater than 30 simple random sample from a population with mean mu and standard deviation sigma. Then X bar means the sample mean, has an approximate normal distribution, mean mu X bar equal to mu, standard deviation sigma X bar is sigma divided by square root of n. Notice the standard deviation of the sampling distribution is also called standard error. The central limit theorem applies for all population. However, for symmetric population, a smaller sample size may suffice. If the population itself is not normal, that means the population is bell-shaped. The sample mean X bar will be normal for any sample size. Decide whether it's approximate to use a normal distribution to find probabilities for X bar. I'm going to the bottom right. A simple random sample of size 24, n less than 30, will be drawn from a population mean equal to 35 and standard deviation equal to 1.2. Doesn't say that the population is normally distributed. Sample size is less than 30. So we cannot use the central limit theorem. Okay. What about the one on the top? Simple, right? Simple random sample of size 8. Very small sample size, but you are drawing it from a normal population. So the sample of size 8 comes from a normal population. You are okay. You can use central limit theorem. Okay. Involving sample means. Okay, recent data from US Census indicates that the mean age of college students mu is 25 years, standard deviation is 9.5 years, simple random sample of 125 students is drawn. What is the probability sample mean age of the students is greater than 26? First, I notice I have to find on the right of 26, and 26 is greater than the mean 25. So I'm on the right of the mean, and I want starting from 26 all the way to the very extreme right, 1E99. So I go second, press the second button, then the worst button, then go to number 2, normal CDF. My lower boundary, I'm starting from 26. My upper boundary is a very large number on the right, which is 1. Then second button and comma button on top of 7 gives me the E exponent 10 and then 99. 1 followed by 99, 0, very large number on the right is my upper boundary. My mean is 25. My standard deviation is not 9.5. It's 9.5 divided by square root of the sample size. So in that step itself, I can do sigma 9.5. Then I press the divided by there, get the slash line, and then square root. How do I get the square root? Press the second button on the top left, then x square, which is halfway down in the first column, gives you the square root, 125. And then go to paste and hit enter and enter. And the answer is 0.1196. 96. So there is an 11.96% chance that the sample mean will be greater than 26. Okay, here sample find the 30th percentile. So the area to the left of the unknown X bar values is 0.3. So second verse, now not 2, because I know the area to the left is 0.3, 30th percentile. So 3, area is 0.3, mean is equal to the mean of the population, 25, standard deviation is 9.5, not 9.5. We are doing a sample of size 125. So 9.5 divided by second, then x square button gives me the square root. Inside the square root 125, I go to paste and hit enter and enter. What does it mean? It means 30% of the score, mean scores will be below 24.55. 30th percentile is 24.55. Based on the data from Hartford Cattle's mean weight of 1-year-old Hartford bull is 11. Mean is 1135. Population standard deviation is 97 pounds. What would be unusual for the mean weight of 100 heads? So you're drawing a sample of size 100, less than 1100. So we want to find the area to the left of sample mean 1100. So second verse 2. Lower is minus 1E99. I'm starting from a very large number on the left. A very large negative number, minus 1E99. Upper, I'm stopping at 1100. My mean is mean of the population, which is 1135. My standard deviation is the standard deviation of population, which is 97, divided by square root of the sample size. I'm drawing sample of size 100. So second x square gives me the square root, inside the square root 100. And I go to paste and hit enter. and enter twice. And that is not 1.54. Probability cannot be greater than 1. So even if you see a number probability greater than 1, there must be something wrong. And that wrong is at the extreme right end of that 1.5, is E minus 4. That means the first number 1 is at the fourth place after the decimal. So actually this probability is 0.000, 3 zeros followed by 1, 0.00015, which is very small, which is less than 0.05. Hence, it is unusual for the sample mean weight of 108 carol to be less than 1100. Okay. Notice they also got 1.54 E minus. Probability, do not jump and say 1.54. Probability cannot be greater than 1. So we have to look at the number. Whenever we see probability greater than 1, we look at the number at the extreme right end, which is minus 4. That means the first number 1 is at the fourth place after the decimal. So it is 0.00015, which is a very small number, less than 0.05. So that event, that the mean weight of 100 head of cattle less than 1100 is not going to happen. It's very unusual. Okay, you can do these problems. We will do one, say we do the second problem. Population mean 47.5, standard deviation sigma is 12.6, sample size 112 is drawn. Find the probability X is between 45 and 48. So second verse 2, lower is 45, upper is 48, mean is mean of the population, which is 47.5. Standard deviation is standard deviation of the population divided by square root of the sample size. So second X square, 112. Okay, paste, enter, and enter. And the answer is 0.6448 or 49. So there is a 64.4% chance or 64.5% chance that the mean will be between 45 and 48. Next question asks greater than 48 on the right of 48. So lower boundary is 48, upper boundary is a very large number on the right. So second verse 2, lower boundary I'm starting from 48, upper boundary is 1, then exponent, second button, then comma button on top of 7, then that gives me the capital E, 99. 1 followed by 99 zeros, very large number on the right. Mean is 47.5. Standard deviation is standard deviation of the population, 12.6 divided by square root of the sample size, which is 112. Paste, enter, and enter. This probability is 0.337, which is much greater than 0.05. Any event with a probability greater than 0.05 is not unusual. So the question is, would it be unusual for X bar to be greater than 48? The answer is no, because that probability is greater than 0.05. So it's a very usual event. Okay, it's not unusual. So the answer is no. So I will stop here today. If you have any question, you can always shoot me an email and I will get back to you as soon as possible. If you send me an email, take care. Have a nice day. I'll see you next time. I'm coming back next time with another chapter, PowerPoint. Okay, take care. See you.